7.6, the natural base e. In the previous sections, we talked about exponential functions and their graphs. Today, we're going to talk about the graph of f of x equals e to the x. F of x is e to the x is like any other exponential function, such as f of x equals 3 to the x. The only difference is the base. Here you have a base of e. E is just a number, an irrational number, like pi. If you plug it in into your calculator, you get 2.71828. It looks like it's repeating, but it's actually not. So let's graph this function. When x is 0, your y is going to be 1. And when x is 1, it's going to be 2.78. We're rounding. Here, the base is greater than 1. So it's going to be exponential growth. So it looks something like this. The domain is all real numbers, and the range is all y's such that y is greater than 0. Now, to find the inverse of e to the x, the first thing we want to do is rewrite it as an equation. So y equals e to the x. Then we want to switch the x and the y. So here we have it as an exponent. Well, we want to turn it into a log. So we can write it as log base e of x equals y. Well, when a log has a base e, it's just the natural log. So we can rewrite it as the natural log of x, and that would be your inverse. To graph it, remember that it's reflected on the line y equals x. So now we're going to have a point at 1 and 0. So it looks something like this. So the domain for the natural log of x, it's going to be the range of e to the x, which is going to be all x's such that x is greater than 0. And for the range, is going to be the domain of e to the x, which is all real numbers. Let's do another example. If we have g of x equals e to the x plus 1, well, this is just the parent function f of x equals e to the x, shifted one unit up. So when x is 0, your y is 2, and when x is 1, your y is 3.7. So it looks something like this. The domain, once again, is all real numbers, and the range is all y's such that y is greater than 1. Now, if we want to find the inverse, we can start by rewriting it as an equation. So y equals e to the x plus 1. Then we switch our variables. So x equals e to the y plus 1. Subtract 1. So e to the y equals x minus 1. Now we want to write it as a log. So log base e of x minus 1 equals y. Remember, when we have log base e, it's just the natural log. So then now for the inverse, the graph is going to be at 2 and 0. And 3.7 and 1. So it looks something like this. Now the domain is going to be all x's such that x is greater than 1. And your range is going to be all real numbers. Now if we want to simplify, all the properties that you guys learned on 7.4, they also apply for the natural log. So if we have the natural log of e to the negative 2t, what I want to do is bring the exponent to the front. So then I have negative 2t times the natural log of e. Remember that log base b of b equals 1. So if we had log of 10, it was equal to 1 because there's a base 10 right there. Well, remember that the natural log is the log base e. So if I have log base e of e, it's just going to equal to 1. So then the natural log of e is always equal to 1. So then here we have negative 2t times 1. It's just going to give you negative 2t. Let's do another example. If we have e to the natural log of t minus 1. Remember the inverse property of logs and exponents? B to the log base b of x is just x. The base b and log b, they undo each other. So the same applies here. So if you have e to the natural log of x, it's just going to be x. Because remember that the natural log is just log base e. So then here, your answer would be t minus 1. Let's do one more. If we have e to the 5 natural log of x, the power property of log told you that log base b of a to the p was equal to p log base b of a. Well, what do we have p log base b of a? Well, we can do the reverse and we can bring it and rewrite it as an exponent. So it would be log base b of a to the p. Well, here we can do the same thing. The 5, we can write it as an exponent. So then we have e to the natural log of x to the 5. The e and the natural log, they undo each other. So then your answer is just x to the 5. In the previous section, you guys learned about compound interest. In this section, we're going to learn about continuously compounded. So the formula would be A equals P times E to the RT, where A is your total amount, P is your principal, R is the rate, the annual rate, and T is the time. So let's do an example. What is the total amount of an investment of 1,000 invested at 5% for 10 years, compounded continuously? Well, our principal is going to be 1,000. E is just E. Your rate is 5%. So if we write it as a decimal, it would be 0.05. And the time is 10 years. When you plug it in into your calculator, you get 1,648.72 cents. In this section, you're also going to learn about half-life. The half-life of a substance is the time it takes for half of the substance to break down or to convert into another substance during the process of decay. Therefore, the natural decay is modeled by the following function. N of t equals 2n naught times e to the negative k times t. Your nt is the amount remaining. Your n naught is your initial amount. And that's when t equals to 0. Your k, that is the decay constant. And t is your time. Let's do an example. The half-life of lead is 22 years. How long will it take for a sample of this substance to decay 80% of its original amount? So in step 1, we want to find the decay constant. That would be our K. So let's start by writing the decay function. N of t equals n naught times c to the negative k times t. Well, your n naught is 1/2. We're talking about half-life. Your n naught would be 1. That would be the life. T would be 22 years. So we can plug what we have into our function. So 1/2 equals 1 times c to the negative k times 22. Well, what I want to do is bring the exponent to the front. So then I'm going to take the natural log of both sides. So ln of 1/2 equals ln of e to the negative k times 22. Now I can bring my exponent to the front. So I have negative 22k times the natural log of e equals the natural log of 1/2. Remember that the natural log of e is just 1. So the natural log of 1/2 equals negative 22k. To solve for k, I divide by negative 22 and negative 22. So k equals 0.0315. Now that we have our k, we can move on to step 2. And now we want to write the decay function and solve for t. So n of t equals n naught times e to the negative k times t. Your nt is the amount remaining, which it would be 80%. If we write it as a decimal, we can write it as 0.8. Your n naught is the initial amount, which is 100%, and we can write it as 1. Your k is 0.0315. Okay, so nt is 0.8 equals to 1 times e to the negative 0.0315 times t. So I want to bring my exponent to the front. Before I do that, I'm going to take the natural log of both sides. So ln of 0.8 equals ln of e to the negative 0.0315t. Now I can bring my exponent to the front. So negative 0.0315t times the natural log of e equals the natural log of 0.8. Remember that the natural log of e is just 1. So the natural log of 0.8 equals negative 0.0315t. To solve for t, I divide by negative 0.0315, both sides. And that's 7.1. So it will take 7.1 years for a sample to decay 80% of its original amount.